You know those old cartoons where the main character steps on a time machine and travels back in time only to accidentally prevent their own birth? Well, that isn't just a plot device in fiction. It's a real problem with time travel. In 1948, physicist and philosopher Kurt Gödel proved mathematically that any consistent physical theory that allows for time travel necessarily contains a paradox. We've all heard of the classic grandfather paradox, which is a thought experiment about what would happen if someone went back in time and killed their grandfather before their parent was born. Obviously, if this were to happen, then they themselves would never have been born and thus would never have gone back in time to kill their grandfather, which would mean that their grandfather would live on to have their parent and so on. This seeming contradiction between traveling back in time to kill your grandfather and the fact that you exist demonstrates something impossible, a logical issue with the concept of time travel itself. But there are other paradoxes too. Say someone goes back in time to save their father from dying in battle, ensuring he comes home and has children, but not knowing that their mother had already met her end in a car crash that would never have happened had their father not gone off to war. By preventing their father's death, the time traveler has unknowingly ensured that their own mother would die, making it impossible for them to be born. So who's right, Gödel or me? Neither. This is known as the grandfather paradox. But just because something is a paradox doesn't mean it can't happen. The grandfather paradox is really more of a thought exercise that illustrates the issues with linear time travel. But it doesn't stop us from daydreaming about going back in time to see dinosaurs or meet historical figures or, kill Hitler or something. And we do have theories about how time travel might be possible. Maybe one day we'll figure out how to build a time machine. But there will always be the grandfather paradox unless, of course, we abandon the idea that time is linear and instead think of it as more like a tree. In a branching timeline, there isn't a single continuous line of events leading from the past through the present into the future. Instead, every decision, every interaction causes the timeline to split, creating alternate versions of reality. So, when someone travels back in time, they aren't changing the past of the world they came from. Instead, they're creating a new timeline in which the changes they make become part of the new universe. In a universe where the traveler kills their grandfather, they might cease to exist. But in the original timeline, they still exist, and so does everyone else. All timelines and universes exist simultaneously. Each possibility is realized in some reality. In this way, even the grandfather paradox is resolved since the traveler simply ceases to exist in one branch while continuing to exist in another. And this isn't just a fun little theory to justify our time-traveling fantasies. Understanding the idea of branching timelines helps scientists explain certain phenomena, like quantum mechanics. Quantum mechanics tells us that all quantum particles exist in multiple states until they are measured, at which point their wave function collapses and they settle into a definite state. Take, for example, the double-slit experiment. When individual quantum particles like electrons are fired through a double slit, they pass through both slits at once, forming an interference pattern on the screen behind the slit. But as soon as we try to measure which slit the electrons are going through, their wave function collapses, and they begin to behave like regular particles going through one slit or the other. They no longer form an interference pattern. For many years, physicists tried to account for this collapse by adding an extra assumption called the observer effect to their theories. Basically, this says that the act of observation causes the wave function to collapse. But the more scientists thought about this, the more problems they found. If the act of measurement causes the wave function to collapse, then why does it collapse when we measure it with an instrument rather than when a person observes it? Does a photo really count as an observation? What about a video camera? What about a dog looking at the screen? These questions led physicists to abandon the observer effect, and instead they began thinking of quantum mechanics as happening in a branching universe. So when an electron goes through the double slit, it actually goes through both at once, but only in some realities. In most realities, it goes through one slit or the other. But in this case, it goes through both. And so when we try to measure which slit the electron passes through, the electron's wave function collapses and it settles into a definite state in our reality, the one where it passed through one slit or the other. This means that in some other realities, the electron continues to go through both slits. But we'll never know about those realities because we exist in the one where it went through only one. The idea of a branching universe is also useful when thinking about black holes. According to general relativity, anything that falls into a black hole is destroyed. There is no coming back out. But according to quantum mechanics, nothing is ever destroyed. Everything has a half-life. So what happens to stuff that falls into a black hole? Some physicists say that it disappears from all universes except for the one in which it continues to exist inside the black hole. This is called the no-hair theorem. Other physicists argue that everything that falls into a black hole gets copied into another universe. In this universe, it takes the same path that it did in the previous one up until the point where it fell into the black hole. After that, the two universes diverge. This means that in this new universe, the object never fell into a black hole. Instead, it was copied into a new universe where it continues to exist free from the clutches of the black hole. This might sound crazy, but it's actually a pretty good solution to some of the problems with black holes, like the fact that they seem to violate the conservation of entropy. Black holes seem to take things from the outside, increasing entropy in their surroundings. But the no-hair theorem says that nothing can get out of a black hole, and therefore nothing can be taken from the outside. So there is no increase in entropy. Now, obviously, this is just speculation. We don't really know what happens inside a black hole or whether or not the multiverse exists. But these theories are useful to understand some of the weirdness of the universe. Theories aside, we have some clues that there are multiple universes. In 1961, an American physicist named Hugh Everett III came up with a theory of his own. He proposed that every time a quantum event occurs, such as an electron going through a slit or a photon being emitted, a new universe is created in which the outcome of the event is different. This is called the many worlds interpretation of quantum mechanics. If this were true, there would be an infinite number of parallel universes where every possibility is realized. In one universe, the electron goes through the left side of the slit. In another, it goes through the right side. In one universe, a photon is emitted in one direction. In another, it's emitted in another direction, and so on. This theory elegantly solves the problem of wave function collapse. There's no need for an observer to cause the collapse. It just happens in every possible outcome. But there's a problem. We have no evidence of other universes. Every time an electron goes through a double slit or a photon is emitted, we can only observe one outcome. Everett's theory requires that we update our understanding of reality. Rather than thinking of these outcomes as happening in other universes, we can think of them as happening in other moments in our universe. Take, for example, the photon being emitted. Either it goes to the left or the right. So there are two possibilities. In this case, the moment after the photon is emitted, there are two distinct moments in reality, one in which the photon moved to the left and one in which it moved to the right. But then the photon interacts with another particle, causing that particle to move either to the left or to the right depending on which path the photon took. This creates four moments, one for each combination of left or right for the photon and the particle. Then the particle interacts with another particle, creating 8 moments, and so on. In this way, every time there's a quantum event, the number of moments increases exponentially. At first, this seems counterintuitive. How can our universe split into an infinite number of copies? But that's exactly what happens. As time goes on and quantum events keep happening, our universe branches and splits until every possible outcome is realized. Everett's theory has some appeal. It neatly resolves the wave function collapse problem without needing to invoke an observer. But it leaves us with an infinite number of parallel universes. Now, that's cool and all, but it's not very scientific. That's because we can't test it. We have no way of observing these other universes or moments, if they exist. In the end, we don't know if the grandfather paradox can ever be solved. Maybe one day we'll figure out how to build a time machine and we'll just have to deal with the paradox when it happens. But maybe the grandfather paradox is just a limitation of our current understanding of the universe. As we learn more, we may find ways to reconcile the idea of time travel with the laws of physics. Or maybe we'll just come up with a new paradox. I don't know about you, but I could really use a good paradox right about now. You know, something to really make me think about the universe and my place in it. It's me. And if you want to help us make more videos like this one, you can join our community on a crowdfunding platform.